So we'll call this, I think we'll call this groundwater. Well, we don't need this. We'll call this groundwater. I have a little problem with my respiratory system, so it might not be, this might not be super audible. Also, I'm wearing this this gaiter so that everyone knows I'm a racist, and so that might make it a little bit less audible too. But anyway, if you have a hard time hearing this video, then turn up the volume. Yeah, it sucks to suck. I'm just going to write down the topics. This is a review video, so we're calling this groundwater review. I'm going to write down the topics for you to review. And by review, I mean this is probably review for those of you who did the explorations and for those of you who were in Earth Science 1, but not review from any other video because we haven't done a video on this because I've been sick in the times that we were going to do it. So the first thing we have on here is aquifer. Now remind me, I'm not going to write all these things down because that's not the point of this video, that's not the kind of video this is, but remind me verbally, what is an aquifer? Like just say it out loud and then I will repeat it for the microphone. We can all kind of be on the same page without going into the detail that we would in a video discussion.
A rock layer that stores your groundwater?
Yeah, it's a rock layer. It's not the water itself. It's a layer of rock that can store groundwater. That can store water. Aquifer, from the Latin aqua, water, and fer, which is related to for, which is to carry. So something that carries water. What do we call it? Remember the three interactions of water with Earth. So what three things can happen when precipitation lands on Earth's surface? There are three outcomes.
Oh, infiltration.
Infiltration, which define that.
It seeps through the ground.
Yeah, it becomes groundwater. That rock layer becomes an aquifer or continues to be an aquifer.
Then there was runoff.
Runoff, where it becomes, the water is now.
Puddle, like it
Yeah.
comes together,
Yeah, we have a general term for all that we did the last two tests on.
Evaporation.
No, that's the next thing. But the what it becomes is surface water. So it's surface water, which can be at first a puddle, and then maybe a rill or a gully, and then maybe a stream or a river, lakes, wide rivers, the ocean. Those are all surface water.
And then evaporation.
And then evaporation, where it stops being liquid water altogether and becomes gaseous water and back in the atmosphere. Remind yourself of the idea of the water table, which is just the interface between the area. If this is the surface of planet Earth, here's a tree to show you it's a surface. Here's Camden. Here's a horse. And this is a short little tree and a short little horse, and this is Camden. And she has pigtails, of course, which are also antennae. Anyway, if this is a layer of rock, we'll say it's sandstone because sandstone makes a good aquifer. Oh, by the way, back to aquifer. What has to be true of the layer of rock in order for it to be able to be an aquifer? Not all rock that has this is an aquifer because not all of it has water. But what makes it able to be an aquifer? What?
Doesn't have to be permeable.
Yeah, it has to be permeable. It has to be porous, meaning it has holes, pore spaces. And it has to be permeable, meaning that those pore spaces are at least somewhat connected so that water can get from one to another, and that makes it an aquifer. And then the water table is this interface between down here. This is all water-bearing rock. The whole rock layer is an aquifer, but down here is water-saturated, saturated rock. And up here, what's true of the pore spaces in this area up here? Yeah, not water saturated. I'm trying to trap you, but that's not what I wanted you to say. What's in the pore spaces up here? No, water's down here. What's in the pore spaces? They have pore spaces. What's?
Frog, plants, roots. I have this in my notes.
Air.
Oh, air?
You were supposed to say nothing, that the pore spaces are empty, but it's not nothing. There's air in there, air saturated. You might even notice sometimes, if it's raining quite hard, the ground will bubble. Like it'll look like Coca-Cola on the ground because the ground's bubbling. That's because very rapidly the air that's in these the air that's in these pore spaces is getting replaced by water, and the bubbles are coming out. The air's coming out of those bubbles. And we have fancy words for this. This is called the zone of aeration. I would write this down if I were anyone with the initials TJ, or even if those weren't my initials, but I would definitely write this down. And then this below it is the zone of saturation. And then the interface between them, the line between those two things is what? The water table. Is the water table always underground?
No.
Yeah, the fact that I asked that makes you realize that the answer is no. The water table is not always. What if I extend this a little bit further, and now this was actually a hill, still sandstone, water table still here, but now look at this. Is it possible for the water table to be above the ground? Yeah. What is this little area right here? Well, on this scale, if that's Camden, yeah, this is like a pond. But yeah, it could be a lake or a pond or a river. We don't know how the water is flowing, but if the water is flowing, it's probably a river. But yeah, if the water table is above the surface of planet Earth, then that is surface water. Oh no, I think my logic capture ended itself. Did you end yourself, logic capture? Is it still recording? It is still recording. We're all good. It's all good. We're still good. Let me see the next thing. Let me pause this and talk to your boy Hunter Owen. I should have coughed before I started it, but here we are. Okay. Was there vocab in your explorations? Okay. I'm going to give you some words, and you tell me if you do or do not know them from your explorations. Geyser. No.
It wasn't a...
Okay. What's a geyser?
It like spews groundwater out.
Okay. Yeah. Groundwater there becomes either surface water or evaporates. But what's happening?
Pressure is...
Yeah. It's built up pressure, and it has to be heated too. In order for it to be geyser, it is heat and pressure. Hot, pressurized water forced through an opening. Okay. Next one. Karst. Is that one of your vocab words? Karst.
Nope.
Okay, well, let's come back to that one. Stalactite and stalagmite.
Yes.
Okay. Stalactite. Stalagmite.
And stalactites are the ones that
Yeah.
Ceiling,
Yep.
and then stalagmites are the ones that are tilted.
Yeah, that's correct. I'm making that face. There's supposed to be a face of humor because the way that I remember them, and this is one of the stupidest things that I remember things as, and I wouldn't even need this anymore because I've been doing this for so many years now. I'm 83 years old and I've been doing this for more than 3/4 of my life. But I could easily do it without this little mnemonic, but the mnemonic that I find helped me, stalactite hangs tight to the ceiling or else it'll fall down, and the stalagmite might reach the ceiling because it gets built up. Usually
I
this...
like mites as in like the bugs.
Okay, mites living on the ground. The stalagmite, since it's made of bloop, 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 usually forms like these kind of, I don't know, I'm not trying to be gross, but kind of like turd structures. Whereas a stalactite is usually pretty pokey because it forms as kind of like an icicle where, I mean, it doesn't form in the same way as an icicle, but it forms the same shape as an icicle because there's already a little point where drips are falling off, and as they drip, each one leaves behind a little bit more of its remainder. And if they ever touch, this is called a dripstone column. I spelled it wrong. I spelled derpstone. It's called a dripstone column, or sometimes just a column. So there you go. You do have this. So a column is when they meet. You know the definition for the words porosity and permeability. I'm going to put them back up here with aquifer. Porosity and permeability. Hey, who lives in a pineapple under the sea, Tristan? Absorbent and yellow and? Porous is he. Porosity is the property of having pores. Some of y'all have a porous nose, you know, and that's... I know from TikTok that people consider that disgusting. I don't know what the big deal is. Everyone has pores. I know that you're supposed to think that large pores are somehow a feature flaw. I don't think that's realistic. But you need to be comfortable with your own body. okay? And you need to be nice to other people about their little bodies, because if you're not going to be nice to people, then they shouldn't be nice to you. Anyway, but to have pores, that property is called porosity, and then permeability is the ability for a fluid to permeate, to get from one place to another. And not everything that's permeable is porous. I mean that the other way around. Not everything that's porous is permeable. Sometimes, in a rock where the pores are completely disconnected, we'll say pumice. That's not always true of pumice, but we'll say pumice. And they're completely impermeable between them. Maybe if this were exposed to the surface, a little bit of water or air can get into here, but it can't get from this one to these ones. Whereas if it's permeable, they're all interconnected. And they can easily get from here to here. So there is a difference between porosity and permeability. And then the test goes quite into depth about what kinds of sedimentary rock would make good or poor aquifers based on these properties, but I'm going to leave that for you to determine. Those are what I would consider depth of knowledge 2 questions, where you have to take your knowledge of sedimentary rocks, or igneous rocks, or metamorphic rocks, and apply that to what you know about porosity and permeability to form conclusions. So those I'll leave out, but I mean, we won't talk specifically about those, just be aware they're going to be on there.
Is this going to be an open note?
Yeah, you'll be able to use your notes, certainly.
Okay.
Definitely your notes. Okay, you know about the water cycle. I'm going to put that on here, but it is still important. The water cycle is in several questions on here. I think we have that on the last 2 tests too, so that shouldn't be a problem, but okay, how does, let's say, let me tell you 2 common misconceptions about aquifer. The first one, the most, I don't know, probably the most egregious one and also the most common. People who don't think about aquifers at all, or people who played Super Mario 64, probably think of aquifers as like a cave underground, where there's just like it's basically like a water bottle that lives underground, and there's water in it, and here's a well, and when you do the well, it pokes into the water bottle, and you can take your yummy water out of there. That is not it at all. There are things that are like this, but this is not how aquifers work. Aquifers work like this. It's all rock. It's more like a sponge than a water bottle. That's how an aquifer usually works. That having been said, we'll talk about the second misconception in a second. That having been said, this can happen. In what kind of rock can this kind of thing happen? Not exactly like, so I'm going to erase it real quick, but... Well, hold up. Tristan, I had a question first. It can. Let's answer Tristan's question first.
So at my grandpa's, there's a spot on a creek where the water runs out of the ground. Everybody's, I don't know.
Like a spring.
A spring.
It is a spring. We'll talk about springs in a second, but bring it up again when we talk about spring. But okay, let's say, first of all, what is that thing? What did I just draw? What would you call this? No, it's not a water bottle. That's wrong. That was a moron said that.
I would call it like a...
Say it.
like a cave?
It is a cave. It is a cave. This is a cave. There are 2 main ways that caves can form. We're going to talk about caves now, so put cave on your list. The word up here behind the picture-in-picture is cave. C-A-V-E. C-A-V-E is how you spell cave. It's behind this. I'm just going to move it so that it can be seen. Boop. There we go. Cave. There are 2 main ways that a cave can form. The first is that I'm going to erase the cave for a second time. The first is that if this is a water-soluble rock, even if the rock is not very water-soluble and it's just a tiny bit water-soluble, this happens over time. And one thing that geological processes are driven by a lot is time. There's lots of time. Is if it's partially water-soluble like limestone. So let's draw the diagram for limestone here. Say this is the sedimentary rock limestone, which is a little bit water-soluble. And maybe it has a tiny fault in it. It can be from roots. It could be from tectonic activity. It can be from someone driving over. I don't know. But there's a tiny little fault in it for some reason. And since the fault is a little bit, it's a crack, so it's lower, has a lower potentiometric surface, any water that falls will eventually get in that crack. And since the crack is in limestone, and limestone is partially water-soluble, the crack gets bigger and bigger over time, doesn't it?
Yeah.
And so it gets bigger and bigger over time, and eventually we end up with a cave, the limestone cave. All the caves that are around here are limestone caves. They're in limestone layers of rock. Another way that caves can form is in really any kind of rock, but it happens most often probably in harder rocks, but sea caves will happen in the same way. Like these are both cross-section views. There's some kind of crack in we'll say it's granite. It doesn't really matter what kind of rock this is, but there's some kind of rock here. We'll say this one's granite, and there's a crack in it. And as the waves, it's a sea cave, and so the waves are constantly hitting this. And as the waves hit the crack, due to a property in physics called impulse, bouncing out of the crack takes more energy from the waves than if it didn't bounce. And so the wave goes into the crack, bounces, and comes back out, and that removes over time quite a lot of rock. And in the same way that from the top down in a limestone cave, from the front in a sea cave, the cave still the opening is fairly narrow, but the cave gets wider and wider on the inside. And this can happen in any kind of rock. But those are the two main ways that caves form. And since this one's happening from the front, this next thing occurs less often, but it can occur in either. And that's where we get this word karst, is that what happens if the cave gets bigger and bigger and Tristan drives his monster truck out onto it?
His monster truck is going to have more chance of falling into
Yeah,
the cave?
yeah. The whole surface can collapse, and now we get this sinkhole. And in areas where this has happened a lot and over a long period of time, we get the idea of karst topography, which is an area on Earth's surface where it used to be caves underground, but now that layer that had the caves has either been uplifted or eroded down enough that the whole surface is just a repeating series of holes. And this is really beautiful. The most famous one of these that I'm aware of is in Singi de Bamaraha in Madagascar. And the ground is like spikes. Like I talked about Mario from Super Mario 64 before. Super Nintendo Mario, the little spikes that kill Mario, those exist in real life. This is just like all spikes. Everything here is just spikes because of what used to be stalagmites, but now it's not even in a cave, and so they're just spikes in the ground. The karst topography is all spiked and really quite dangerous. And if you go hiking there, you have to be really careful. And you even have to. They give you some like, I don't know, like not chainmail, but like Kevlar gloves, so that when you're climbing, you don't rip your hands all up. Can I help you, young man? This is not algebra, but thank you for yeah. You might have been confused because you saw some letters here, but it is in algebra. I think. Oh, we still need to talk about springs, Tristan. But also, check out this picture back over here about Camden and the horse. This is the second misconception that people have about aquifers. Where did this water come from? A lot of people, I wouldn't say mostly farmers, but because farmers do think about groundwater quite a lot because they irrigate, a lot of people, including farmers, have this misconception that the groundwater is just kind of a static amount. Like the Lord put the groundwater there and that's it. That's all we've got, like your bottle of water, and if you drink it all gone, it's all gone. But where did this groundwater come from? Some of it certainly is primordial. Some of it has been there for an awful long time, certainly in some areas. Some of it may have been there for millions of years. But in general, where does the groundwater come from?
Rain.
Rain. Yep. Infiltration. Infiltration. And this process of water, precipitation, infiltrating the ground and becoming groundwater is called recharge. Just like when you recharge your phone, the aquifer is recharged by precipitation. There's also this idea of what's sometimes called the water budget, where as long as the water we use is less than the amount that's recharged, we're going to be okay. There's going to be a net increase in the water in the aquifer. But that's not the problem with that what I said is a fine philosophy. But the problem with that is that people forget that there are all kinds of other outlets of water. A plant that's growing takes water from the ground and releases that into the air. And so the point is, you can't ever completely tally up all the debits from the water budget, all the things coming out of the groundwater, and so you're never going to get an accurate statement of how much needs to be recharged. The real balance is no human withdrawal. Like, that's the real water budget. If humans aren't using it at all, that's the correct natural balance. But obviously people need to drink water. And so I'm not saying that it's bad, just that the idea of a water budget is usually skewed to make people feel better about themselves and isn't an actual reflection of reality. I think as I'm looking through these, the rest of these are all primarily things that you should be able to, from this information and from the stuff we've learned previously in the year, you should be able to draw a conclusion. Acid rain real quick, and then we'll talk about springs. What makes an acid? What is an acid? You're not wrong. It's just that's very vague. Acid is something that will release a hydrogen ion when it's dissolved in water. And so acid rain happens when water falling through the sky interacts with some other molecule. For instance, carbon dioxide will make very, very, very lightly acidic rain. The rain that falls normally in pure air is maybe something like 6 to 6.5 on the pH scale. 7 is perfectly neutral. Even though it's more or less pure water, it has fallen through carbon dioxide, and so the chemical reaction H2O plus CO2 yields H2, actually we should say, Lily, is in equilibrium with H2CO3, is happening all the time as rain falls. So water, the rain, falling through the little bit of carbon dioxide that's in the air produces carbonic acid, H2CO3. The same thing that makes, a similar thing to what makes the bubbly water in your Coca-Cola bubbly, is H2CO3, carbonic acid, which will release a hydrogen ion when it's put into water, which it is part of the water. And this is a very light acid or very weak acid, but it is acidic enough that it will dissolve the limestone over time, like back in this diagram. The problem becomes when we get things like sulfur trioxide or any kind of nitrous or nitric oxide in the air, then we end up with stronger acids. So for instance, if we have sulfur trioxide in the air, we end up with sulfuric acid, which is a strong acid and is much better at dissolving things. Or same thing with nitrogen dioxide, we get nitric acid. Sorry, it should be that. And that's not balanced, but both of these are a much larger problem for what's called acid rain. And then, go ahead.
I was gonna say, let's balance it for fun. Just kidding, I don't do that.
I might have, the reason we're not going to is because I might have written this equation wrong, and you can't balance a bad equation, so this might not even be balanceable, but let's try it. I can tell this is already going to be problematic. Does that do it? No, definitely not, because that has to be multiplied. Maybe this? No. I don't think that can be balanced because I think I did a bad job writing it. Just forget about that one. Look up the real equation for extra credit. Anyway, not right now. I do want to talk about springs. Look, right here, this guy is a spring. This little point right here is a spring. And there are different kinds of springs. But a spring is any place where the groundwater is becoming surface water. Where water is flowing out of the ground and onto the surface is a spring. And there are lots of different kinds of springs, and they usually have to do with the location of the water table as it relates to what's called an aquiclude, which does not allow water to pass, or is sometimes called an aquitard, which slows down water, but we don't want to say a word like that. That's what it is, that's its real name, but an aquifer can carry water. That's what it means. An aquitard will allow water to pass, but only exceedingly slowly, and an aquiclude does not allow water to pass. So in two examples here, if we have, let's say, this is called a perched spring. But let's say we have these two aquicludes here, which will not allow water to pass, and then these two aquifers. As the whole place recharges, you'll see this gets a water table, and this gets a water table. But since this is a perched water table, the water will eventually flow out of here and down to here, and you'll see this little like stream constantly flowing from here down to there. That's one way that it can happen. Another, and I think a cooler way, is called an artesian well, which is where we get this layer here is an aquiclude, meaning the water can't pass. This is an aquifer, and this is an aquifer. Oh, I think it has to be open on the ends here. Yeah, it does. So this can happen. What might cause something on planet Earth's surface to look like this? If we're looking at this both cross-section again, but if we're looking at this and we have these three layers in this arrangement, what might have caused that to happen? Because we know with no kind of outside influence, their original horizontality, one of Sino's principles, but they're originally like pancakes. They're in straight file line. Why might it someday be like this?
It got like erosion.
Erosion probably wouldn't do this because they'd still be in straight lines. They'd just be like, it'd be like you took a spoon and took a bite out of a stack of pancakes. So they'd still be in straight lines. But what can do this is some kind of tectonic activity or faulting. Maybe there was even a sinkhole that caused the whole thing to collapse down like that. But for whatever reason, now these are in this orientation. And so as the recharge occurs, maybe the water table gets way up to there. So down here, this is all filled in with water. Now, what's really cool about this, something happened with oil too, and this is where if you ever, I don't know, I was first aware of this from like Bugs Bunny, but like in California when they were finding oil, sometimes they drill down and the oil would spurt out like in a really, really tall geyser. It wouldn't be a geyser because that has a different definition, but it'd be a really, really tall spurt of oil. What did they call it? I can't remember, but anyway, the reason that would happen sometimes is for this exact same reason. They'd find basically an artesian well of oil, but it's going to happen with water too, because the water table height is actually here. And so if you're down in the valley, this could be this could be a house. Like this could be very, very large scale. But if you drill a well down into this, the water pressure is at that height, and so this will erupt water. Oops, I should have drawn that in blue. This will erupt water all the way up to the height of the water table. And so you get this, what's called an artesian well, which is pressurized water because the water table is higher than the land here. But unlike here, where the water table is higher than the land, there's no surface water because it's just the whole thing is aquicluded by this aquiclude. So you get this really tall, beautiful, pressurized spring. And this might be what when people think about a spring, unless you are familiar with one in real life that was like this, people might think of this, like a place in the ground that really just like spurts up pressurized water.
So my grandpa, my mom always told me to drink right from that. Is that
Yeah, this should be, it wouldn't be pure water, like it wouldn't be like distilled water. It would certainly have some dissolved particles in it, but it would be more or less sterile. Like the only little microbes and stuff that might make you sick in it would be coming from the ground itself, like right where it comes out. So if you were just like holding your cup up to, if this were solid rock, for instance, like if it was dirt and mud and
no, 'cause it goes from
cow crap and
rock.
stuff, you wouldn't want to do it there. But if it was solid rock, sure, just as your water comes out.
It goes like rock and then
Yeah.
Um,
There's a place in Hot Springs where you can get, there's a spring right there and you can just fill your little cup right out of
what's
the
that thing called?
water.
The water.
Artesian well. I'm sorry, I should label these. So this is a perched well. I'm sorry, perched spring. And this is a artesian spring, which is a different word than artisan. Artisan means it was made by an artist. Artesian means this kind of spring. You can buy water at Walmart for like 50 cents as artesian water.
The Continental Divide
Oh yeah.
in Colorado. I mean, this is a little different because obviously it's surface water, not groundwater. But when the snow is like melting in the summer and stuff on the top of the mountain, you can just hold your cup under it
Right.
and drink the water. And
Should
it's
be.
really good water.
Yep, that should be, like I say, relatively pure. I mean, it wouldn't have a chance for microbial growth is what we really use to determine the quality of water. Obviously, things like the chemical components we test for the Know Your Well program, those can degrade the quality of water to some extent. But if it's more or less pure water from the rain falling down and doesn't have a chance for microbial growth, it should be roughly pure water.
I'll remember to bring it in tomorrow, but my dad gave
Yeah.
Because he says that it makes him feel like really sick, and so. does
I
it.
love
That's
railroad
all.
water, but it is weird.
Yeah.
They get it,
Some of them.
unless they've changed
Yeah.
this, I think they get it from the Mississippi
Is it the
River,
one that is like
and
tiny little
and they
ball?
just
Yeah.
do reverse osmosis to just some water from the Mississippi River. Anyway, last thing, just to talk about wells briefly. A well is what we, and I've alluded to this before, but I'm going to use this picture of Camden up here. A well is what we call it when we somehow drill down into the water table and then pump water up out of the water table. That's called a well. And as we do that over time, the water table will sink around this called well drawdown. And this pattern, in 3 dimensions, it's a cone, and so we call it, and this is the coolest thing. I think this is the sickest thing in all science. We call the cone, that shape of a cone of well drawdown, we call it the cone of depression. And so, cone of depression. That's a good name for a band. I say this every single year, and no one ever starts up a band called the cone of depression. But that area where the well has drawn down the water table. And what you see the problem. If you overuse this well, eventually the water table will be lower than the well itself, and you won't get anything out of your well. And so that can definitely happen as the water table lowers. In fact, it happens around here. People's private wells, as the water table lowers, get less and less water at first quality, and then eventually their water stops. They don't get any water at all out of the ground.
Thank you.
The test also goes into depth a little bit about pollution. There's several questions on here about pollution. As long as you understand how the water is flowing in this system, the questions about pollution should be fairly easy for you. I think that's everything. I mean, there are a few things that I left out, but they were intentional, and there's several things that I talked about throughout that are on the test, but they're really opportunities for you to combine information from this with information from the past. So, you have any questions or any questions you think Marissa might have?